The state of matter called gas is vital for our everyday life. While running or walking, we can all relate to the feeling of moving with or against the wind. We breathe air to intake oxygen and exhale carbon dioxide, a vital process for our life. It's easy to imagine the feeling of the wind and the fresh air outside of the city. Everywhere you look, from cars to factories to the boiling water in your kitchen, all of these things dispel some form of gas. In the late 1700s and early 1800s, learning how to manipulate steam to do work led to radical shifts in the way we organize ourselves economically. The invention of the steam engine not only transformed our economy, but it transformed the physics community as well. We saw an explosion of interest in understanding the bulk properties of gases and other forms of matter. This shift saw the birth of thermodynamics and later statistical mechanics, looking for more efficient designs to the workhorse of the economy, the steam engine. Steam engines even today provide the majority of electric power we use every day. It's from this perspective that we see modeling and understanding gas affects not only our understanding of our everyday experiences, but also aids in humanity's ongoing quest for more efficient and green energy production. Today on this channel, we take our first step towards modeling gases by considering the simplest possible case, the ideal gas law. Hey, what's going on everyone? My name is Jonathon Riddell, and today we're going to talk about the ideal gas law. In particular, we will first derive the Grüneisen law, and then for this video, we will then employ the equipartition theorem as a quick solution to the problem arriving at the ideal gas law. In the next video, we will fully develop the problem, however, and derive the energy term from statistical mechanics. To get right into it, we need to remind ourselves about the thermal probability distribution function. We say that the probability that a system connected to a thermal reservoir has energy Ek is given by the following formula. 1 over Z is a normalization constant ensuring all probabilities sum to 1, and beta is the inverse temperature. We call Z the partition function. If you want more intuition or an explanation for this probability distribution function, my video on Jaynes' principle of maximum entropy shows how one arrives at this formula. It's quite straightforward, and if you haven't seen it, I'll leave a link in the description. We're going to need a formula that links the expected value of energy strictly to the partition function. It turns out that this is quite easy. The energy can be rewritten as the negative of the derivative of the natural logarithm of the partition function with respect to the inverse temperature beta. That's quite the mouthful. We are keeping volume fixed here, of course. This simple formula is generic, and we will use it a few times in our exploration of the ideal gas law. When we say ideal gas, what we are implying is that the interactions between the particles are unimportant, which means the only contributing energy that we will consider is the kinetic energy. In this video, for the sake of employing Grüneisen's law, we will consider this problem quantum mechanically. The system we will have is non-interacting particles in a cubic box where the only restriction is that the particles cannot escape the box. Most of you have probably seen this in an introductory quantum class. The energies for a single particle end up being written in the following form, where h is the Planck's constant, n1, n2, and n3 are positive integers that index our energies. M is the mass of our particle, and of course L is the side length of the box. Throughout the video, we will regularly write the vector n as a label for n1, n2, and n3. This is as far as our quantum treatment goes. We will not consider whether these particles are fermions or bosons, but we will consider them to be indistinguishable. That is, we will have to face the fact that we cannot tell which particle is which. They are all identical. Returning to the language of macro and microstates, we are working in a regime with the thermal distribution, which tells us that specifying the number of particles in our box, big N, the temperature, T, and the volume, V, this completely specifies our macrostate. The microstates, on the other hand, are equivalent to specifying the vector n for every single particle in our box. By supplying all 3 times big N quantum numbers, or all of the little n's, we can calculate the energy of our microstate. We can think of this energy as being some constant c divided by the volume to the power of 2/3. This observation will become important soon. We're now in a position to derive Grüneisen's law. Here we are interested in energies of the following form. Alpha here is just a representation of all of the n vectors for all of the particles in our system. So we have alpha as the index of our energy, and we say that the energy as a function of volume can be written as some number c alpha divided by the volume to the power of some number x. This allows us to write the partition function as a sum over all c alphas, like this. But the key here is that the partition function is just some function of the inverse temperature beta times the volume to the power of negative x. We can then use this fact with our expression for energy. Plugging this function into our formula for energy, we then use the chain rule and the rule to take the derivative of the natural logarithm of a function to arrive at a seemingly messy formula. But we actually only need one more ingredient to combine this with to arrive at Grüneisen's law. The last ingredient is that the Helmholtz free energy is related to the partition function through the following formula. It is the negative of the Boltzmann constant times the temperature times the natural logarithm of the partition function. This was derived in our video on Jaynes' principle of maximum entropy, again, a link in the description. Borrowing from thermodynamics, we see that the pressure is defined as the derivative of the free energy with respect to volume, keeping temperature fixed. This again gives us quite a messy formula with the function f and its derivative for the pressure. But looking at our energy formula and our pressure formula side by side, we note that if we divide them out and then rearrange, we arrive at Grüneisen's law. The law states that the pressure times the volume equals some constant x related to the scaling of energy times the energy. Note that this derivation relied quite heavily on the form of the energy, so one needs to be careful when applying it. Putting everything together, we remember that our energy E had the following form. As mentioned before, this gives us an x of 2/3. So Grüneisen's law tells us that we have pressure times volume is equal to 2/3 times the energy. If you've seen the equipartition theorem before, or you know the average energy per particle for classical kinetic energies or something along these lines, you might be guessing where we can go next. Now, for the sake of the length of the video, we will employ the equipartition theorem to finish off our proof of the ideal gas law. The equipartition theorem says that for every degree of freedom we have, which appears quadratically in the energy, has an average energy of 1/2 times the Boltzmann constant times temperature. Since we have n particles and we have 3 dimensions to explore with kinetic energy, we can write the overall energy as 3/2 times the total number of particles n times the Boltzmann constant times temperature. Plugging this all back into Grüneisen's law gives us the ideal gas law we all know and love. It's important to note, though, that the equipartition theorem fails in a number of cases, and by using it, we have assumed, for example, that temperature is reasonably high in this scenario. At smaller temperatures, for example, quantum effects can become much more important, and the theorem might fail. So this is the end of part 1. In part 2, we will calculate the energy without appealing to the equipartition theorem. This will give us a nice look at how calculations can be done in the framework of statistical mechanics. As always, guys, thanks for watching. If you liked the video, feel free to like, subscribe, and leave a comment below.